All right, everyone, welcome back. Today is lecture 2 of Particle on a String, our introduction to rotation, and we're going to take this easy by working in 2 dimensions. 3 dimensions is somewhat more difficult. This is, I hope you just try to absorb as much of this as you can. This is the easy part. You should be able to handle all the mathematical thises and that's that we're going to do with 2 dimensions, 2-dimensional rotation. We talked about that last time. Our particle, an electron, is attached to a string and it's being spun around and around and around. Now that means that the radius is fixed. Really difficult when you allow the radius to change. You have to do that for like a hydrogen atom, but for now the radius is fixed. So I'm spinning something around and the radius is fixed. So it's on like a rigid string, I guess. And we have to solve the quantum mechanics for that. Now, last time I showed a little image here of how to think about the wave functions, which ones are allowed or not. And from that, we were able to calculate the energy. And we did this just by figuring out what are the allowed wavelengths. From the wavelengths, we got the momentum, and momentum squared over the mass, over 2 times the mass, is the energy. That's how we did that. Now we let's see, what did we get? We got the energy was equal to m squared, h bar squared, over 2 times the mass times r squared. Okay. Now we just talked about this last time, but it bears quite a bit of examination. The first thing we found was this m is a new quantum number. Now, this is stupid, but it's something we have to deal with. Unfortunately, it is traditional to call this quantum number m. Just like we had n for our particle in a boxes and even Planck distribution, number of modes and all that, we use the letter n. For rotation, for 2-dimensional particle on a string, we use the letter m. That is very unfortunate because we're used to m being mass. This is one of the stupidest things we've ever done as scientists. We have 2 m's. Okay, there's not much I can do about this. If I don't call it that, if I decide to make it up, make it something else, then you don't know what's on your standardized exams if you're going to take standardized exams. If all of a sudden the letter m appears, you think it's mass, then you're kind of screwed over, aren't you? So I have an obligation to show you how it's done, but try not to get confused. M, as we talked about last time, 0 plus or minus 1, plus or minus 2. And of course, just like the n quantum number of the particle in a box, the reason that we found this thing is because of the number of nodes in the wave function, right? The higher up you go, the more nodes there are. Now there's a plus and minus because the energy has m squared. So it doesn't matter if it's minus. And I also mentioned last time that when you think about rotation, you can rotate 2 different ways. So this m tells you whether you're going clockwise or counterclockwise, whether it's plus or minus. I don't know which one's which. I assume plus is clockwise, and it doesn't matter. Okay. Now, one of the ways that we try to get around this problem of too many m's is that we call mass times r squared the moment of inertia. So mass disappears, and instead we see the letter I. Okay, so look, I think this is still very unfortunate, and I have this. I've always put like what's wrong questions. I try to make you trip up m versus mass, m quantum number for rotation versus mass. I will try to trip you up on that because I'm telling you right now, well, that's not fair, but I'm telling you I'm going to do it. So that actually is, that's like more than fair. But again, the people who aren't watching are the ones who are going to miss. So there you go. Let's see. All right, now I wanted to spend just about 5 minutes. You've had physics 1. You had to have physics 1. Physics mechanics, right? Velocity times time is distance and all that. Now you had rotation. Now, let me be the first to say that I hate rotation. I hate it, I hate it, I hate it. I hate angles. I hate atans. I mean, tangent is bad enough that an atan, what the hell is that? Yet, we have to, this is the world we're going to be in for several more weeks. Everything we're going to do from now on are going to be in cylindrical and spherical coordinates, r, theta, and phi. We will not escape them until this class is over. So we're going to have to get used to them. In that regard, I want to remind you about the basic physics mechanics of rotation, right? So that it kind of gets things like, oh, all right, okay, that's what theta is, and that's what J is. And, okay, what's a J? I already mentioned a J. Okay, we call angular momentum is J. That's just a traditional, instead of a P for what is technically linear momentum, I've just been calling it P. For angular momentum, it's called J. Now, we're still in 2D. Now, that means that this type of momentum that we are working with is Jz. It is the Z component of the angular momentum. Now, why is that? Okay, now hold on one second. Let me point out that we proved this last time, that this is MHR, where M, again, is 0, plus or minus 1, plus or minus 2. We technically proved that last time when we figured out what the wavelength, what the allowed wavelengths are, and then we plugged that into the de Broglie relation for wavelength versus momentum. So we solved the momentum. Right. Angular momentum. I should have mentioned that was angular momentum. Let me remind you what this is, in case you forgot. I'm not going to bring this up again. I could, but let's think of, okay, this is y and this is x, because remember, we're going to have to start converting between x and y here. But let's think of something's rotating, it's rotating, it's rotating. Okay, let's stop here. Okay, now there is, of course, an r vector, and in the particle on a string, it's fixed, so it's like a nanometer. Right, so we'll make that easy. And now remember, like one of the things you learned as a kid is that you always think that if you're spinning something around and you let go, that it goes outward, and it doesn't, right? It goes in a straight line, right? So that's like one of the first things you learn about physics as a child. So you know the momentum isn't outward, which a particularly stupid 5-year-old would think. Instead, you know the momentum is straight. So that's the linear momentum, right? So that's technically P. Right? That's the linear momentum. And you can tell because it's moving in a line. Now, the angular momentum is these are vectors, right? Cross P, right? Remember cross products? Because I don't. Every time I have to do a cross product, I have to look up the formula. I freaking hate cross products. I hate tangents. Anyway, here we are. We have to get used to this. So momentum is R cross P. Okay, I do remember one thing about cross products. It's that right-hand rule, right? Just that, God, I hate that right-hand rule. I hate tangents. I hate all this. Anyway, I shouldn't be saying that. I'm going to have to edit that out. Right-hand rule for angular momentum. Now that means that the angular momentum vector is not in the same plane as R and P. R and P are the xy plane because we're doing the two-dimensional particle on a string. And that means that J is in the z direction. So that's why I call this Jz. So let me draw that because I know that can be a little confusing. Oh, you know what? Let me remind you. Remember this formula for cross product? Absolute value of the vectors, sine of the angle between them. Sine is 90. These are always at 90 degrees, right? So that's 1. And then, of course, the normal vector as determined by the right-hand rule, which we know to be in the z direction. However, is it plus or minus? Right. So let me try to draw this. So I'm going to take this and I'm going to tilt it because you can't see the z direction unless I do that. And I have to practice this, by the way. This is not easy for me. So this is x and y. Doesn't really matter. Okay, so this thing is rotating this way. And so what that means is that, in this case, the momentum vector is the plus z vector. So there you go. Now you're thinking like, well, wait a minute, of course it is. You know, that's the right hand rule. Versus, now let me do it again. Again, I'm going to try to draw the x and y best I can. All right, you know what I'm going to do this time? It's going the other direction. Gotcha, gotcha. So in that case, then you're in the minus z direction. Okay. And this is also why you have m quantum numbers that can be positive or negative. Right? So all of this kind of works together. It all makes sense. And you don't really even need to memorize any of that. Okay, so one thing that's kind of neat about this is if you look at this formula here, if you consider that the angle, as I've drawn it, is 90 degrees, this ends up being r times the momentum. And the momentum, I've already told you, is m h bar over r. Right? That was the linear momentum from earlier lecture, and that means that this is mh bar. Right? Just like I had just kind of stipulated that before, but this is the proof. Okay, and then the last bit, energy from, and again, what I'm trying to do, I know I'm kind of repeating myself, but I'm using the language of physics mechanics. I'm showing that this is consistent with the stuff we've already done. This is why I may appear repetitive, but again, from physics mechanics, you should have learned that in 2 dimensions, the angular momentum squared over 2 times the moment of inertia is the rotational energy, and therefore this is m squared, h bar squared over 2I. Which, again, is right here. I'm reminding you of what we just kind of figured out cleverly just based on those little graphs I drew. So, again, review of physics mechanics, right-hand rule, stuff that we did the other day from that nice little graphic I made that took me a couple hours. And notice how about every bit of this, it's all saying the exact same thing. We're actually kind of lucky. Quantum sometimes will not do this, but when it comes to 2-dimensional rotation, all this stuff, everything works the same way. That's kind of a saving grace. That's kind of a saving grace because it gets a little bit more complicated as of right now. Let's solve the wave functions using pure mathematics. All right, so everything I've done right now, I've basically done the particle on a string problem using hand-wavy, oh, let's figure out the wave function from a piece of paper folded in on itself. Oh, let's check what physics, physics mechanics, physics 101 says. Oh, everything's the same. That's great. But again, as I just said, quantum may decide to go its own way. And that means that we have to double check this. We have to do this using the Schrodinger equation. I mean, I haven't really used the Schrodinger equation yet, have I? So that's not right. Now, it will give us all the same things, and that's why this is a good way to start, but it will get more complicated, and obviously I mean when we get to 3D. Now, to start on the Schrodinger equation, we have to be in not spherical coordinates, we're going to be in cylindrical coordinates. That means that z doesn't exist. I know the angular momentum is in z, but all the action is in x and y. That is technically what cylindrical coordinates are. So let me remind you what cylindrical coordinates are, and I think I remember I learned this my junior year of high school, so I know it's probably been a while. And, okay, let's say y is up, x is left and right, and let's draw an angle. Okay, and this is kind of important. The angle in x and y is phi. Now, theta will be this deal. Theta's that deal. Don't worry about that. That's coming up in 1 or 2 lectures. This is phi. Now, the reason I am dramatically emphasizing this is because mathematicians switch those. Physics and chemists use phi, just like I've done, but mathematicians would call this theta. I don't know why. It's unbelievably stupid. But if you look on any internet, this and that, for these, for this stuff, depending on whether it was written by a mathematician or not, you will see those angles switched. Every time I'm like, trying to make lecture notes or a homework problem, and I'll look on the internet too, just to, get some idea, make sure, double check things. I always have to make certain that the definition of theta and phi are correct. So look out for that. Okay, anyway. What's sine? That's the opposite over the hypotenuse, right? So I'm not going to write that down. So that is, of course, this is r. So that is, so it's, I always do it that way, right? So it's the opposite one over the hypotenuse. And the opposite one, the length, would be in the y direction. The hypotenuse, of course, is length r. Remember all this stuff? Okay. Now with that, you can figure out that y is r sine phi. And x, of course, will be r, that's cosine, right? Yeah, r cos. For the same reason. Remember that cosine is adjacent over hypotenuse. So adjacent would be in the x, the length is in the x direction. R, okay, so these are my Cartesian coordinates. Now let's switch to spherical. Spherical only has r and phi. So r, of course, is, you would have to have something seriously wrong with your memory to not recall that r is square root of x squared plus y squared. I'm assuming that you know that. And here is that freaking tangent. I will hate tangent my whole life. I just hate it. It's y over x. And it just is. Okay. Well, that, of course, means that the angle itself, so, I like the fact that going, we're used to x and y, so now we have to convert that to r, which is not hard, but the angle is a bit of a biz knocker. So the reason that ATAN is just such a nightmare is that we're going to have to be doing calculus with tangents and atangents. So we're going to have to do derivatives of atangents. I have no idea how to do that. I had completely forgotten. I do remember how to look it up on the internet, which works. So on your homework problems, you can look up the answer on the internet, right? So, and I tell you that. I'll even, give you identities and whatnot. All right, so this is all fine and good. This is just a walk down memory lane. Hopefully, maybe even some of you remember this. Now, let me point out the problems that we're trying to get the Schrodinger equation. Now, the Schrodinger equation has a bunch of constants, and we're in 2 dimensions, so that means that we've got to deal with this thing. Right? We've got the double derivative of x and the double derivative of y. But we can't work with x and y, because in a thing with spherical symmetry, x and y just don't work. So we want to convert our x and our y to an r in a phi. Now, hopefully you've figured out enough that you can't just say double derivative of r plus double derivative of phi. That would be really nice, but it's going to be more complicated than that. Actually, in this case, it'll end up being pretty simple for 2-dimensional particle in a string to convert this to r and phi. But when we go to spherical in next lecture or the lecture after, it will not be easy. All right, so just heads up on that. It's funny how these things like blow up. Okay, now what do I want to do? Let's do one of these terms, so r and phi. So how do we do that? How do we convert a derivative of x and y into derivatives of r and phi? Now notice that this is not a Jacobian problem, right? This isn't the change in x. This is the derivative of x, actually a double derivative. Those are not the same. Partial of x and derivative of x are not the same thing. It ends up being a little bit more complicated. All right, not terribly. Again, this one's kind of easy. Let's start with x first. Chaining. So that's how you do this. And I generally have questions like this on the homework and the exam. And I will give you the formulas like this formula, the chain rule formula. Okay, so notice how clever this is. Partial x, partial x. You can think of it like this. Just cancel out the partial r, partial r. There's a partial r on top. There's a partial r on the bottom. Cancel them out, you end up with ddx. Right? You see? And that ends up being kind of easy. Now this is just, now this part, despite all my partial this, partial that, this is just a simple derivative. This is the change in r with respect to x. And I've got a formula for r. This is obviously going to be a little on the complicated side. I hate saying square root of a function. So then it's 1/2 the, God, I'll figure it out. I hate to see functions inside of functions when I'm doing derivatives, but it can be figured out. So that's a derivative. Okay, now you have to do the same thing with phi. You know, you hope you were done, right? But then we do the derivative of phi with respect to x. And again, this is a derivative, and I told you we were going to have to do the derivative of a tan. There it is. Okay, so that's the problem. Let's see, how do I want to do this? I need a little bit more room, so tell you what, let me wipe out the board. I'm going to move that up, and then I'm going to work the whole problem below. So give me 1 minute to wipe out the board, and we'll finish this up. All right, so I took a little inspection of the camera, and I believe that you can still see this, this little expression on top for what we're going to do to solve this. Okay, so I'm going to take that for granted that you know that, let's see here, we need to figure out the change in r with respect to x. Okay, so what is that? That is the change, and so we're going to degenerate to a pure math class here for a second. And recall that when you're doing multivariable calc, I know you hadn't had it, but it's stupid. Just treat the y like it's a constant because this is the derivative with respect to x. Right? So there's nothing to it. Okay, now, God, function in a function. Hate that. Anyway, so this is a function to the half. Okay, so that means you bring down the half, and then you've got the function to the 1/2 minus 1. So now it's the function to the minus 1/2, right? So I've got that square root on bottom. And again, the y is just a constant. Okay, but then you got the thing that kills you, right? Is then you do the derivative of the inside, which is 2x. Okay, well now the 2's go away, that's cool. It's a little bit easier. Okay. Okay, so I can obviously simplify this a little bit. Oh, wait a minute, the 2's are gone, right? X, oh look at that, that's r. Square root of x squared plus y squared is r. However, I've made a mistake. The mistake is to stop here. I can't stop here. I cannot stop here because our mission was to get rid of the x's and get rid of the y's. We're doing x now. Our mission was to get rid of the x's, and I haven't. I've got an x up there. I got to get rid of them. There can't be any more x's or y's. The solution to that is when we were covering what are spherical coordinates, and things, in fact, I hope it's in the screen you can see that x is r theta phi, r cosine phi. I'll write it all out. Sorry, that looks awful. That bothers me. There we go. There we go. Ta-da. Now again, the important thing is that when we convert the kinetic energy operator into cylindrical coordinates, there cannot be any x's and y's. Okay, next one. So let's do, and as I mentioned, we're going to have to do a tan. And I looked this up. I have no, I don't know what an a tan is. I don't even know what it is. I know I can Google what is the solution, what is the derivative of a tan, and it gives me this. Thank you, Internet. All right, whatever. As before, I've got x's and y's, and I can't have that. Okay, y is minus r times sine. Okay, so no more y. and on the bottom is r squared. So that ends up being minus sine b over r. Okay. The point of this is that looking at the original function for the change with respect to x, it is cos phi change with respect to r minus sine phi over r minus sine over r. My notes are wrong. Good thing I just caught it. Take me forever to fix it digitally. Okay, so there you go. There is the change with respect to x, and here's the change with respect to y. Going through the same process. And, you know, there's always this odd symmetry to this. Turn the cosines into sines is one of them. All the pluses turn to minuses. Now, don't presume that. I'm just saying it always seems to want to do that. It seems to. Sometimes I'll run into if I'm doing more complex calculations, sometimes I don't see that. But there's usually there's always a change, but the changes are always kind of very similar. There we go. I wanted it to look nice. So there you go. So now I've changed, taking a derivative with respect to x and y, and I've translated those to cylindrical coordinates. Okay, this is all fine and good. But the next thing is that we're not doing single derivatives, we're doing double derivatives. Okay, now that, unfortunately, I've put those on homework questions before, and I have a video that shows you how to do that. But to be honest, it actually is really way more complicated than it looks. When I had a problem set in years past, I had a problem set 6 or 7, I can't remember which one, was devoted to doing the double derivative of x and y in r and phi. It was the entire problem set. It ends up being a lot more complicated than you think. Tell you what, let's just not worry about it. If you can follow along here, I'm pretty happy about that because it shows, again, remember, math skills are logic skills. It means that you can take the function of a part and then translate that to a function of another part, which is built on the first one. That's an unbelievably good skill. Now, you're doing that with a bunch of letters, but if you can do that with machines or the human body, you are truly a useful person. Right? So again, this is why every profession, when they're looking at your metrics, like if they want to see your transcript, they're looking at your math scores. That is what they want to know. Because it doesn't matter what field you go into, that's the #1 predictor of success. Now, if you're thinking, well, that's too bad for me, I'm not even going to try, that's why some people make money and some people don't. I just want you to know, that is a choice that you make. Always know that. Your decision to not work on your math is the decision to not make as much money as you could. That's your decision. Live with it. Not a good choice, but then again, some people are rich and some people are not. So, remember, I grew up in a housing project, right? I told you that a zillion times. Okay, well, I'm not preaching. What is the answer? Okay, let's see. All right, let me wipe this out here. Let me just write it out. And it actually is going to simplify because remember that this is a particle on a string, and the string we assume is rigid. So that's why if you look at that video I have linked, if you really want to see it done, I'll show you the whole thing. You don't need to. You don't have to watch it. I'm not making you do that anymore. But just if you really want to know how it's done, you do have access to that information. I mean, it's Google. You can Google it too. I Googled it to make sure. Of course, I worked it out, but I Googled the answer to make sure I had done it right. So you see, it's a little bit more complicated. It looks a little bit more complicated than just double derivative of x plus double derivative of y. That's not particularly scary. This is a little bit more complicated. Except for the following. Get this. This is kind of cool. I'll say it. But R is fixed. So So it's like this. Let's say that the wave function, remember that this will be separable into a wave function for r and a wave function for phi. Let's say that the wave function for r is like 1 nanometer. In other words, this is a particle on a string, and the string is 1 nanometer. Now, I don't know if this is like a wave function, if this is like a legit wave function, because, you know, a wave function is just equal to a nanometer. That's not much of a function. But the reason I want to point that out, for 2 reasons, is that it points out that in this model problem that we are working on right now, the particle on a string, the radius is fixed. So this emphasizes that. Now it does another thing. What is the derivative of a function with respect? What is the derivative of a function that's a constant, right? Here's a derivative, and it's going to act on a constant. What's that? 0. Okay, so if the wave function in R is constant because the radius doesn't change, then these 2 terms get wiped out. They'll always be 0. And therefore, the Hamiltonian can simply be simplified to just the, sorry, that doesn't look good, to simply the double derivative with respect to phi. So there you go. That ends up simplifying things quite a bit. Now, what that means is, here, I'll just point this out. What that means is that now I'm ready to write out the Hamiltonian, and hopefully you'll recognize that you've seen it before. Okay, let me take my time though and point out big picture. I just want to make sure. I want to make sure that you understand that this is something you know. Remember, I have to write out mass from now on because there's another m now. So this is what you know. We were just talking about it literally just moments ago. And what it turns into is minus h bar squared, 2 times the mass, times 1 over r squared. You see, it actually simplifies. And these we combine into the moment of inertia. Again, that only works because r is constant. So you see, it actually ends up being kind of easier. So that's kind of nice, and that's why we always start with the particle in the string. All right, now what do we do? Okay, tell you what. We've got the Hamiltonian defined. Now we have to solve it. And as always, that is our Eigenvalue Equation. And this is one of the few times that we can actually figure out the wave function using the Schrodinger Equation. Remember how we keep just coming up with it on our own? Just like, oh, look, it's a sine wave, right? We can't, I can say that without using the Schrodinger Equation. This time I can actually use the Schrodinger Equation. Okay, let me point out that we've already figured out the energy. And because it's a little spherical deal, it has to be, that classical calculation we did earlier works. H bar squared m squared over 2i. Now, before I then write down the wave function, let me point out that actually all of this is, you've actually seen all this before. So you've seen the wave function before. Look at this. Constant's double derivative with respect to a single variable. H bar squared, something squared over 2 something. See, it's a free wave. Remember I said that the particle in a string has parts from a particle in a box. That's what we began with. The piece of paper that was folded over. Those were particle in a box wave functions. So it's part particle in a box and it's part free wave. This is the free wave part, right? This is basically the first Hamiltonian you saw on day 1 of quantum mechanics. Instead of an x, there's a phi. That's the only difference. That makes it 2-dimensional. But it's still the same damn thing. It's just it's got a phi instead of an x, and instead of an m, you have an I. Those are just letters, right? Instead of h bar squared k squared, I've got h bar squared m squared. Those are just letters. What does that matter? right? So you can see these are basically the same thing. And as a result, the wave function now, which of course will not be a function of x, I almost wrote an x, it will be a function of phi, is guess what? It is, where am I? E to the I m phi. Right? It's like a forward, instead of e to the I kx, it's e to the I m phi. Wherever there's a k, there's an m. Wherever there is an x, there's now a phi. That's about it, and it's all the same. Now, let's see here. Let's double check. All right, let's go back here. That's h bar squared over 2y. Double derivative. Always double check. I had you do that on that last exam. Here is the wave function. Okay, so I'm going to pick up an I squared m squared. I squared is minus 1, so that gets rid of the minus sign. M times m is m squared, 2i. There you go. Oh, it's not an eigenvalue equation unless I write the function again. There you go. And for the zillionth time, there's the energy again. Okay, so I hope you find that's kind of neat. Now I have the wave function. And I've got a couple more things to mention about this. Let me just tell you real quick that what we're going to do now is we're going to go into, we've now got the solution, and now we've now got the wave function. We already know the energy, but like when we did vibration, now there's like a whole bunch of things I can do with the wave function. So we're going to do that part now. Now, real quick, because some of you may have noticed this, e to the I m phi was like e to the I kx. Notice that there was a solution of e to the minus I kx. Well, that's okay because m, remember m can be plus or minus 1, plus or minus 2, on and on and on. So e to the plus or minus I kx, e to the I m phi, I define m as being plus or minus. So there you go. So your e to the I plus or minus I kx, you can see that you've got e to the plus or minus I m phi. So again, it's the same. Heads up. I will explain this in a moment. But notice that you may be thinking like, oh, sine and cosine are okay too, just like the free wave. Those are not okay. There's some differences, all right? It's not perfect. E to the plus or minus I m phi, e to the plus or minus I m k, those are all valid for their respective problems. But unlike the free wave, where sine and cosine were okay, sine and cosine are not okay with this one. I just wanted to point that out. I'll explain that more in a minute, but I need to cover some other aspects. I'm going to do things with the wave function, and then I'll circle back and explain why that is. I just wanted to make sure that you understood why I'm not writing down sine or cosine. Anyway, what I want to let's see, what can I cover first? Let's see here. It's more than a page, that's why I'm confused. Okay, so remember how we solved K when we were doing all those particle hitting the barrier things? It's always 2m e is square root of 2m e over h bar squared. Okay, so for m, we can figure that out too. It is plus or minus square root of 2ie over h bar squared. Okay. Now, this is where this gets kind of funky, right? So I've just done the same thing I've done before, right? So tell you what, now I feel kind of bad about this. So we know that this is energy. This is energy, right? So I want to make sure you know where this comes from, right? So 2i over h bar squared is equal to m squared. And therefore m is plus or minus. There you go. However, remember when we were talking about that folded piece of paper, and I just said it a second ago, it's in fact right there, I don't know why I'm writing it down again. M is a whole number. It can be negative or whatever, 0, 1, 2, minus 1, minus 2. Now look at that. Now, isn't that a heck of a thing? Now I can understand 1 and 2 real easy. I've understood 1 or 2 since I was 5 years old. But this function, 2ie over h bar squared, square root, that thing has to be 1, 2, 3. So what you're seeing is quantization. Just like particle in a box, right? You've got a quantum number that dictates that there are certain discrete energy levels that satisfy boundary conditions. Here, you can see that not any energy will do. Remember that when I talked about how wave functions, the energies of the wave functions have to make sense? This is an example. The energy has to basically eat up these other constants such that this expression is a whole number. Now, it can only do that if energy has discrete values, which is the quantum of quantum mechanics. So that's just one kind of interesting aspect of this. And let's see, I don't know. And then I wanted to point out one last thing about why this is. I showed you why m was a whole number because it was related to the number of nodes in the particle in the box wave functions when we folded them over on itself. Remember that a little while ago? There's another way to show that m has to be a whole number now that we know that it's part of the wave function. And how that works is the following. Let me wipe this out. Oh, I'm on the wrong board. Tell you what, give me a moment to wipe out the board and I'll be right back. Okay, we're back. Here is the reason that m has to be a whole number, other than the reasons I just showed. Think about, it's related to the quantization of the energy. Think about the particle in the box. The particle in a box had only certain energies that were allowed because the wave functions had to have nodes at the ends, right? The wave function was, the ground state's a half sign because it's 0 at the endpoints. Those were boundary conditions. The boundary conditions meant that not any wave function is going to work. And because not any wave function works, you can't just have any energy. And that's where we got the expression of energy for the particle in the box. We have a boundary condition here. That boundary condition will also restrict the energies. And that manifests itself by having m being 0, 1, 2, 3, or minus 1, 2, 3. All right, so again, that's the big picture. Now let me write down the boundary condition. And what that is that if you spin all the way around, you go back to the beginning, right? A little different than the particle in the box, which is that you have to be 0 at your endpoints. Here, you have to bite your tail, right? 0 at the endpoints for particle in the box, have to bite your tail for the 2D rigid rotor. Okay, so what does that mean? See, now that I have the wave function, I can now do this. And this, of course, is e to the IME, e to the, let me make sure I'm doing this right, 2 pi IM. And I just used a identity. And it's got to be equal to its original self. And the only way to do that is if either the 2 pi IM is equal to 1. Not close to 1, sort of 1, but 1.000. Okay. Now you go look at some Google. Go Google this for a bit and look for identities of E2 complex numbers. And you find that this is equal to 1 only if m is 0, plus or minus 1, plus or minus 2, ... Okay. Now remember that since energy is h bar squared m squared over 2i, let's see, now let's take a big picture look. Boundary condition, you have to bite your tail. Some simple maths. Here's the condition restated, just it's fleshed out a bit, it's a little bit easier to see. Google tells us that m's have to be whole numbers. That is how you satisfy the boundary condition. But because this guy ends up being our quantum number, as usual, the quantum numbers always seem to show up in the energy. And now I can see that energy can't just take any value. h squared over 2i, and m is going to be 0, 1, 2, or 3. So there's discrete energy levels. Okay, so that's how you do that, and maybe I could put something like that on the exam. And last bit here. I know I'm almost out of time. I'll have a little bit more to say, but I'll save it for next time. I want to mention why sine. So here's the question. I mentioned this a while ago. So why is I'll say sine. Sine kx. I say m instead of kx. I've got mv. No. Why is that? Why cannot you have a sine or a cosine? I won't say cosine. I mean, you get it, sine or cosine. Like a particle in a box, particle in a box was okay with sine and cosine because a sine is a particle moving left and right. Now, you don't know which direction it's moving in, and so you have to model the particle, the free wave particle, as moving left and right at the same time. It's not doing that, you just don't know which it is. Now, e to the ikx plus or minus e to the minus ikx is sine and cosine. That's why it was okay for a free wave, because you didn't know whether the particle was moving left or right. Now, the analogy here for an angle is that you don't know whether the particle is moving clockwise or counterclockwise. If that was truly the case, then sine and cosine would be okay. But they're not okay, and here's the answer. You are always allowed to know which way the particle is rotating. So whether this or this, the great turkey that lives in the sky that created this two-dimensional universe and this string and this electron spinning around on it cannot deny this information to you. If this is what you have, you can experimentalize which way it's going. You can know which way it's going always. So you cannot justify a sine or a cosine. Now let me explain why. Okay, now I have to go back to a free wave. I have to go back to a free wave. But let me remind you that a photon energy is hc over lambda. Now, kinetic energy is p squared over 2m. And that has, if we're talking about that free wave particle absorbing the energy of a photon, then the momentum imparted is 2mhc over lambda. Okay, so what's going on here is I've got my free wave particle, and it's absorbed a photon. Why did it do that? Because I'm trying to figure out whether it's moving left or right. Okay, fine. So it absorbs a photon. Now, the particle will pick up kinetic energy. That's the only energy it has. And therefore, the momentum it picks up is that thing there. However, the momentum of a photon is from, we figured out, is h over lambda. See that? No, they're not the same. Okay, so once again, particle, free wave particle. You don't know whether it's moving left or right. So you try to shoot light at it. And actually, I lied to you earlier, it won't absorb the light. Because if it does, it has to pick up this momentum. That momentum has to be accounted for by the photon, but it doesn't have that much momentum. So what happens is that the particle doesn't absorb the light. It can't, because it can't absorb the energy and the momentum at the same time because they're not the same thing. You would violate one of the conservation laws. Either you can conserve energy, but you won't conserve momentum. You could take the opposite approach. You can conserve momentum, but then you would find that you don't conserve energy. So what the particle does is, knowing that it will break a fundamental law, it chooses not to absorb the photon. So that's the resolution. So a free wave particle cannot be interrogated by light. It won't absorb light, and therefore you can never know whether it's moving left or right. But it turns out that a 2D rigid rotor, we're going to do a problem on this later. It turns out that you can know whether it's moving left or right. Moving clockwise or counterclockwise. I have to change my language. It's all the same thing. It turns out that you can figure out whether a particle on a string is moving clockwise or counterclockwise. It can absorb light. Now, I'm going to have you prove that in a problem that's coming up in a while. It's actually one of your last problem sets when we get to spectroscopy. But I just wanted to say, and I'm out of time, that this is why sine and cosine are not acceptable wave functions for the particle in a string, because if the Great Turkey said, I've got a particle on a string, but I'm not going to tell you which way it's turning, you have the option of shining light on it and determining spectroscopically which way it's going. So you can never justify a model that lacks that knowledge. So that's why the wave functions are always easy IMV. Right-handed or minus, either the minus IMV, which is left-handed. Okay, anyway, I've run out of time. I think I went a little over. Sorry about that. Next time, we're going to review a couple more tidbits. I'm sorry I didn't quite finish this. We're going to cover a couple more little tidbits on particle in a 2D string, and then we're going to get to three-dimensional. So the three-dimensional, this is the two-dimensional rigid rotor. We're going to get to the three-dimensional rigid rotor next time. All right, I'll see you all then.